Everything you see began in a single, unimaginable instant. We are going on a journey to the very edge of understanding, exploring 30 of the most profound questions about the formation of the universe itself. By the end, you will grasp the full cosmic story, from a flicker of quantum energy to the distant fate of all existence. We will ask what sparked creation and whether time itself had a beginning. We will confront the invisible forces of dark matter and dark energy that dictate our destiny. What do you believe lies at the absolute foundation of reality? Our first question is perhaps the most fundamental of all. What was before the Big Bang? The name itself is a little misleading. We are not talking about an explosion in a dark, empty void. The Big Bang describes the moment when all of space and time, and all the energy and matter within it, erupted into existence from a state of unimaginable density and temperature. There was no outside for it to explode into, there was no before for it to follow. Space and time, as defined by our physics, were born in that event. Asking what came before the Big Bang is like asking what is north of the North Pole. The very framework of before and after breaks down. This is where our intuition, built in a world of cause and effect, hits a wall. Yet, scientists and thinkers cannot help but push against that wall. Some theories suggest our universe is part of a cyclical process, a cosmic bounce where a previous universe collapsed in a big crunch only to rebound in a new Big Bang, an eternal cycle of death and rebirth. Others propose a multiverse where our entire cosmic history is just one bubble in a frothing, infinite sea of other universes, each with its own laws of physics. And some interpretations of quantum gravity suggest that time, as we experience it, is not fundamental at all, but emerges from a more basic, timeless reality. This question forces us to confront the very limits of our knowledge. It is not just about the origin of stars and galaxies, but about the origin of existence itself. The search for an answer, or even the realization that there might not be one we can comprehend, defines the very edge of human curiosity. This leads us directly to our second great mystery. If the Big Bang was the beginning of space and time, what could have possibly triggered it? What was the spark that ignited the cosmos? The idea of a first cause is a monumental challenge for cosmology. In our everyday world, every event has a cause that came before it, but at the instant of the Big Bang, there was no before. So we must look to realms of physics where our everyday rules do not apply. One compelling idea comes from the strange world of quantum mechanics. In the quantum vacuum, empty space is not truly empty. It is a seething, bubbling sea of potential. Particles and their opposites, matter and antimatter, spontaneously flicker into and out of existence, borrowing energy from the universe for a fleeting moment before vanishing again. These are called quantum fluctuations. Some theories propose that our entire universe could be the result of one unimaginably vast and stable quantum fluctuation in a pre-existing, timeless void. In this view, the universe literally appeared from nothing, a random but permanent bubble of something emerging from the quantum foam of nothingness. It did not need an external trigger because the rules of quantum physics allow for such spontaneous events. Another family of theories suggests there was no true beginning at all. Perhaps our Big Bang was not a start but a transition. The cyclic universe model imagines a previous cosmos that collapsed under its own gravity in a cataclysmic big crunch. But instead of ending in a singularity, the immense energies and densities caused a rebound, a cosmic bounce that launched a new phase of expansion, our universe. In this story, the trigger was the death of a prior reality. There are even more exotic ideas involving higher dimensions. Our three-dimensional universe could be like a membrane or brain floating in a higher dimensional space. A collision between two such brains could have released colossal energy, sparking our Big Bang like two sheets of reality crashing together. Each of these models is an attempt to answer the unanswerable, to find a cause for the first effect. They push our understanding of reality to its breaking point, asking us to accept that the origin of everything might lie in a realm of pure probability, a forgotten cycle, or a hidden dimension. The search for the trigger is not just about finding a mechanism. It is about deciding whether the question, "Why is there something rather than nothing?" is one that science can ever truly answer. The sheer energy of that first moment would forge the very laws of physics. To understand the universe in its first second is to witness a reality more alien than any science fiction. Conditions were so extreme that the four fundamental forces we know today, gravity, electromagnetism, and the strong and weak nuclear forces, were fused into a single, unified superforce. This was the era of grand unification, a state of perfect symmetry where matter and energy were indistinguishable. For a fleeting fraction of that first second, during what physicists call the Planck epoch, the entire observable universe was compressed into a space trillions of times smaller than a single atom. The temperature was beyond comprehension, soaring above 10 to the 32 degrees Kelvin. At such energies, space and time themselves lost their smooth, continuous nature and became a chaotic, frothing quantum foam. Then something monumental happened. As the universe expanded and cooled, this perfect symmetry began to break. The single unified force splintered. First, gravity peeled away, defining the fabric of spacetime itself. Then the strong nuclear force, which binds atomic nuclei together, separated from the electroweak force. This release of pent-up energy triggered a phenomenon that would dictate the fate of everything to come: cosmic inflation. In an unimaginably brief flash, from about 10 to the negative 36 seconds to around 10 to the negative 32 seconds, the universe did not just expand, it underwent exponential, faster-than-light inflation. A region of space smaller than a subatomic particle was stretched to a size larger than our entire observable cosmos today. This inflationary burst solved several profound puzzles. It explains why the universe appears so remarkably flat and uniform in all directions. It smoothed out any initial wrinkles, ironing the cosmos into a nearly perfect blank slate. But on the quantum scale, tiny fluctuations were inevitable. These microscopic ripples in the fabric of space-time, magnified to cosmic proportions by inflation, became the seeds for all future structure. Every galaxy, every star, every planet you see today grew from those infinitesimal imperfections imprinted in the first trillionth of a second. By the time the first full second ticked by, the universe was a vast, seething primordial soup. It was still far too hot for atoms to form, but the stage was set. The forces had taken their modern forms, and the blueprint for the cosmic web was already written into the expanding fireball. The universe had moved from a state of pure, undifferentiated energy to a place where structure and eventually complexity could begin. That brief, violent burst of expansion solved two of cosmology's greatest puzzles in one stroke. The first is the horizon problem. Look at the cosmic microwave background, the afterglow of the Big Bang, in opposite directions of the sky. The radiation from these two regions has almost exactly the same temperature. This is strange because, according to the standard Big Bang model, these two patches of sky were never close enough to exchange heat and reach a common temperature. They were beyond each other's cosmic horizon, forever out of touch. It is as if two cups of coffee, placed in separate, isolated rooms, somehow cooled to the exact same temperature without ever communicating. The theory of inflation provides an elegant answer. It proposes that these distant regions were once intimately connected, crammed together in that tiny, pre-inflationary speck. They had plenty of time to equalize their temperature before inflation violently stretched them apart, locking that uniformity into the fabric of space itself. The second puzzle is the flatness problem. Measurements show that the overall geometry of our universe is remarkably flat, like a perfectly stretched sheet. This is a very precarious balance. For the universe to remain flat for over 13 billion years, its initial density at the Big Bang had to be fine-tuned to an astonishing degree of precision, like balancing a pencil on its tip for eternity. Any tiny deviation would have caused space to either rapidly curve in on itself or expand into a hyperbolic shape long ago. Inflation naturally explains this perfect flatness. Think of blowing up a balloon. As it inflates, any small wrinkle or curve on its surface becomes stretched and smoothed out, making the balloon appear larger and flatter. In the same way, the inflationary expansion stretched the fabric of the universe so tremendously that any initial curvature was smoothed into the flat geometry we observe today. Our strongest evidence for inflation is etched into the cosmic microwave background. While this ancient light is incredibly uniform, sensitive telescopes have mapped minute temperature variations, tiny hotspots and cold spots that differ by mere millionths of a degree. These are the magnified quantum fluctuations from the inflationary epoch, the seeds from which galaxies would eventually grow, but the evidence goes deeper. Inflation predicts a very specific pattern for these fluctuations, a statistical signature that matches the observations almost perfectly. Furthermore, it predicts that inflation would have generated primordial gravitational waves, ripples in spacetime itself, which would leave a distinct swirling pattern in the polarization of the cosmic microwave background. While this definitive signal has not yet been conclusively detected, the search for it is one of the most active pursuits in modern cosmology. What could have possibly powered such a fantastic expansion? The leading idea involves a hypothetical energy field called the inflaton field. In the earliest moments, this field was trapped in a high-energy state, like a ball perched at the top of a hill. This state exerted a tremendous negative pressure on space itself, acting as a kind of anti-gravity that drove the exponential expansion. As the universe cooled, the inflaton field slowly rolled down its energy hill. When it finally reached the bottom, this stored energy was released in a fiery burst, reheating the universe and filling it with the hot plasma of particles that would eventually form everything we see. The exact nature of the inflaton field remains unknown. It is a placeholder in our equations, a ghost in the cosmic machine. Various models propose different shapes for that energy hill, leading to different durations and strengths of inflation. Some even suggest inflation could be eternal, with new pocket universes endlessly budding off from a greater multiverse. While the details are debated, the core idea of a rapid, smoothing expansion in the universe's first moments has become a cornerstone of our cosmic story, transforming a universe of mysterious fine-tuning into one whose properties arise naturally from a single, breathtaking event. That fiery burst of energy from the end of inflation filled the cosmos with an almost unimaginably hot, dense plasma. For hundreds of thousands of years, the universe was an opaque fog, a searing sea of particles where light could not travel freely. Electrons, positively charged protons, and other particles were so energetic that they constantly scattered any photon of light, trapping radiation in a chaotic dance. Then a profound transition occurred. As the universe continued to expand and cool, it finally reached a temperature low enough, around 3000 degrees Kelvin, for electrons to be captured by protons, forming the first stable hydrogen atoms. This moment is known as recombination. For the first time, the fog lifted. Photons, which had been trapped for eons, were suddenly set free. They began streaming across the universe in all directions, unimpeded. This first flash of liberated light, stretched and cooled by 13.8 billion years of cosmic expansion, is what we detect today as the cosmic microwave background. It is the oldest light in existence, a snapshot of the infant universe when it was a mere 380,000 years old. This discovery was one of the greatest accidents in scientific history. In the mid-1960s, two radio astronomers at Bell Labs, Arno Penzias and Robert Wilson, were troubleshooting a strange, persistent hiss in their sensitive horn antenna. This noise was constant, coming from every direction in the sky, and it would not go away no matter what they did. They even famously cleaned out pigeon droppings from the antenna, thinking it might be the source. The hiss remained. Unbeknownst to them, a team of Princeton physicists led by Robert Dicke had been actively searching for this very signal, a predicted relic glow from the early universe. When the two groups connected, the realization was electrifying. Penzias and Wilson had stumbled upon the smoking gun evidence for the Big Bang theory. For this accidental discovery of the cosmic microwave background, they would later win the Nobel Prize. This faint microwave whisper is the single most important piece of evidence we have for the hot Big Bang. It blankets the entire sky with a nearly perfect uniformity, glowing at a frigid temperature of just 2.7 degrees above absolute zero. Its incredible smoothness tells us the early universe was a remarkably homogeneous place, just as inflation predicted. But the story does not end with smoothness. In the 1990s, NASA Cosmic Background Explorer satellite, followed by the Wilkinson Microwave Anisotropy Probe and the Planck spacecraft, made exquisitely detailed maps of this ancient light. They revealed that the cosmic microwave background is not perfectly uniform. It is imprinted with tiny variations in temperature, minuscule hotspots and cold spots that differ by only about 1 part in 100,000. These are not flaws, they are the cosmic blueprint. These faint ripples are the direct descendants of the quantum fluctuations magnified by inflation, regions of slightly higher and lower density in the primordial plasma. Gravity would spend the next billions of years working on these imperfections. The slightly denser patches where the cosmic microwave background is a tiny bit warmer acted as gravitational seeds. They pulled in more matter from their surroundings, slowly growing over cosmic time into the vast web of galaxies, clusters, and cosmic voids we see today. Every structure in the universe, from the grandest supercluster to our own Milky Way, can trace its origin back to a specific pattern in that ancient light. By studying the precise statistics of these temperature variations, cosmologists can read the cosmic microwave background like a history book. It tells us the universe's age, its composition, its geometry, and even the amount of dark matter and dark energy present at that early epoch. It confirms that ordinary atoms, the stuff of stars and planets and us, make up less than 5% of the cosmic budget. The cosmic microwave background is our most direct line of sight to the universe's infancy, a fossilized echo of creation that still whispers its secrets to anyone who knows how to listen. The liberation of light was just the beginning of a new chapter. With the cosmic fog cleared, the universe entered a long, dark era. But long before that darkness fell, in its very first minutes, the cosmos was already busy building the first pieces of matter. This brings us to our sixth great question: how did the first elements form? The story is called Big Bang nucleosynthesis, and it is the universe's first and most fundamental act of alchemy. For a brief window of time, starting about 1 second after the Big Bang and lasting for roughly 20 minutes, the entire cosmos was a perfect, searing nuclear furnace. The temperature had cooled enough from the initial inferno for protons and neutrons, the building blocks of atomic nuclei, to exist as stable particles. But it was still unimaginably hot and dense, like the core of a star but filling all of space. In these extreme conditions, nuclear fusion could occur on a cosmic scale. Protons and neutrons began to collide and stick together. The first and simplest fusion reaction created deuterium, a heavy form of hydrogen where a proton and neutron bind together. Once deuterium nuclei formed, they could fuse further. Adding another proton created helium-3, a light isotope of helium. Collisions between deuterium nuclei could create helium-4, the most common and stable form. This was a frantic, universe-wide race against time. As the cosmos expanded, it was also cooling rapidly. The density and temperature were plummeting. By the time about 20 minutes had passed, the universe had expanded and cooled so much that the average energy of particles dropped below the threshold needed to overcome the electrical repulsion between positively charged nuclei. Nuclear fusion slammed to a halt, the cosmic furnace shut down. In that narrow 20-minute window, the universe cooked up almost all the helium that would ever exist. According to the precise predictions of Big Bang nucleosynthesis, about 25% of the ordinary matter in the universe by mass should be helium-4. The rest, roughly 75%, should remain as plain hydrogen, single protons that never fused into anything heavier, and there should be only trace amounts, vanishingly small quantities, of deuterium, helium-3, and lithium-7. This is not just a theoretical guess, it is a stunningly precise prediction. When astronomers look out at the oldest, most pristine regions of the universe, at gas clouds that have never been inside stars, they measure these elemental abundances. The observed amounts of primordial helium and deuterium match the Big Bang predictions with breathtaking accuracy. This agreement is one of the three great pillars of evidence for the Big Bang model, alongside the cosmic expansion and the cosmic microwave background. It tells us that our understanding of physics during those first critical minutes is correct. The process stopped because the universe simply became too big and too cold too quickly. There was no time to build anything heavier than lithium. The nuclei of carbon, oxygen, iron, and all the other elements that make up planets and life required a much more powerful and sustained forge. That job would be left to the stars, which were still hundreds of millions of years away from igniting. So when you look up at the night sky, remember that the hydrogen in every star and the helium that fuels its fusion were forged not in a stellar core, but in the first fleeting minutes of all existence, in a furnace that was the entire universe. The universe was now a vast, dark expanse filled with a sparse soup of hydrogen, helium, and a ghost. That ghost is our next great mystery. What is dark matter, and how did it shape everything we see? For all the triumph of Big Bang nucleosynthesis, a shocking truth emerged. The atoms forged in those first 20 minutes, the stuff of stars and planets and us, account for less than 5% of the cosmos. The rest is dark, unknown, and governed by a substance that interacts with light only through gravity. The evidence for dark matter is overwhelming and comes from multiple, independent lines of sight. The first clue appeared in the spinning of galaxies. In the 1930s, astronomer Fritz Zwicky noticed that galaxies in distant clusters were moving far too quickly. The visible mass of the cluster was not nearly enough to hold them together with gravity. They should have flown apart. Decades later, Vera Rubin and Kent Ford made an even more precise measurement, studying the rotation of individual spiral galaxies. They expected stars on the outer edges of a galaxy, like our own Milky Way, to orbit more slowly than those near the center, just as Pluto orbits the Sun more slowly than Earth. What they found was astonishing. Stars at the very edge of galaxies orbit just as fast as those near the core. This means there must be a tremendous amount of invisible mass, a vast halo of dark matter extending far beyond the visible stars, whose gravity is whipping those outer stars around. Without this invisible anchor, galaxies would simply tear themselves apart. The second line of evidence comes from gravity's ability to bend light itself, a phenomenon called gravitational lensing. According to Einstein's theory, massive objects warp the fabric of spacetime. When light from a distant galaxy travels past a massive cluster of galaxies, its path is bent like light passing through a lens. By studying how the images of background galaxies are distorted, astronomers can map the total mass of the foreground cluster. Time and again, these maps reveal that the vast majority of the mass is not in the glowing galaxies we see, but in an immense, diffuse cloud of dark matter enveloping the entire cluster. The third and perhaps most compelling evidence is written into the cosmic microwave background itself. The precise pattern of hot and cold spots in that ancient light is a detailed record of the universe's composition at 380,000 years old. The size and distribution of those spots tell us exactly how much ordinary matter and how much dark matter were present. The data fits perfectly only if dark matter outweighs normal matter by a factor of about 5 to 1. This invisible substance was not a late addition. It was the essential architect of cosmic structure from the very beginning. In the early universe, dark matter had a crucial advantage. Normal matter, protons and electrons, was coupled to light. The intense radiation pressure from the primordial plasma pushed against the clumping of atoms, smoothing out any attempts to form structure. Dark matter, however, does not interact with light at all. It is immune to that radiation pressure. So while normal matter was being buffeted by photons, dark matter could begin to clump together under its own gravity almost immediately after the Big Bang. It formed an invisible cosmic scaffold, a vast network of filaments and halos. Only later, after the cosmic microwave background was released and the universe became transparent, could normal matter fall into the gravitational wells created by these dark matter structures. The hydrogen and helium gas streamed along the dark matter filaments, pooling at the intersections where dark matter halos were densest. There, it could finally collapse, ignite, and form the very first stars and galaxies. In a very real sense, every galaxy we see is just the visible tip of a much larger, darker iceberg. We are living in the bright, dense knots of a shadowy web we cannot see. We know it is there because of the gravitational pull it exerts on everything around it, shaping the cosmos on the grandest scales. Yet, after decades of searching, we still do not know what it is. It is not made of atoms. It does not emit, absorb, or reflect light. It simply is, and its silent gravity wrote the blueprint for the universe. While dark matter sculpts the cosmic web, an even more enigmatic force controls its ultimate destiny. This is dark energy, and its discovery shattered one of the most fundamental assumptions in cosmology. For most of the 20th century, scientists believed the universe's expansion, born from the Big Bang, was gradually slowing down. The collective gravity of all the matter in the cosmos, both seen and dark, should have been acting like a cosmic brake, pulling everything back together. The only question was whether that gravitational pull was strong enough to one day reverse the expansion in a big crunch, or if the universe would simply coast toward a cold, quiet halt. Then, in the late 1990s, two independent teams of astronomers made a measurement that turned everything upside down. They were observing a specific type of stellar explosion called a Type I, a supernova. These explosions are remarkably consistent, acting as standard candles whose true brightness is known. By measuring how dim they appear from Earth, astronomers can calculate their precise distance. By also measuring how much their light is stretched or redshifted by the expansion of the universe, they can determine how fast the universe was expanding when that light was emitted billions of years ago. The results were shocking. The most distant supernova, whose light had been traveling for billions of years, were fainter than expected. This meant they were farther away than the standard model of a slowing expansion predicted. The only possible explanation was that the expansion of the universe was not slowing down at all. It was speeding up. Some mysterious repulsive force was overcoming gravity's pull, pushing galaxies apart at an ever-increasing rate. This force was dubbed dark energy. Think of it as the opposite of gravity. While gravity pulls matter together, dark energy seems to be an inherent property of empty space itself, causing space to stretch apart. The numbers are staggering. According to the latest measurements, dark energy constitutes about 68% of the total energy budget of the universe. Dark matter makes up about 27%, and all the stars, planets, gas, and dust, everything we are made of and can see, comprises less than 5%. We are living in a universe dominated by forces we cannot see and do not fully understand. So what could dark energy be? the leading candidate is something Einstein himself proposed, then famously discarded, called the cosmological constant. This is the idea that empty space is not nothing. It has an intrinsic constant energy density. As the universe expands and more space comes into existence, this vacuum energy increases, driving the expansion faster and faster. It is a simple, elegant idea baked into the equations of general relativity. The problem is when physicists try to calculate the expected strength of this vacuum energy from quantum theory. The number they get is wrong by a factor of 1 followed by 120 zeros. It is arguably the worst prediction in the history of science. This colossal mismatch suggests we are missing something profound. Alternative theories propose that dark energy is not constant, but a dynamic field that changes over time, nicknamed quintessence. Perhaps it is a fifth fundamental force that has only recently begun to dominate the cosmos. Or maybe our theory of gravity itself, Einstein's magnificent general relativity, breaks down on the scale of the entire universe. The identity of dark energy is the single greatest mystery in modern physics because it dictates the ultimate fate of everything. If dark energy is a true cosmological constant, as current evidence suggests, the future is a lonely, cold, and dark one. The acceleration will continue forever. In tens of billions of years, distant galaxies will be pushed away so fast that their light can no longer reach us. Our observable universe will shrink to include only our own gravitationally bound local group of galaxies. Stars will eventually burn out, and the cosmos will become a vast, expanding void of isolated stellar corpses and black holes, growing colder and darker for all eternity. This is known as the heat death or the big freeze. If dark energy is something more exotic and grows stronger over time, it could lead to a truly apocalyptic end called the Big Rip. In this scenario, the repulsive force would eventually overcome all other forces, first tearing apart galaxy clusters, then galaxies, then stars and planets, and finally ripping apart atoms and the very fabric of spacetime itself. The fate of the cosmos, from an eternal freeze to a violent shredding, hinges on the true nature of this mysterious energy that fills the emptiness. We are passengers on a ship sailing into an unknown future, driven by a wind we cannot feel. That blueprint of dark matter, written into the faint ripples of the cosmic microwave background, was the universe's only guide through a profound emptiness. After the release of that first light, the cosmos entered a period known as the Cosmic Dark Ages. For hundreds of millions of years, the universe was a vast, silent sea of neutral hydrogen and helium gas. No stars shone, no galaxies glittered. It was a place of profound darkness, illuminated only by the fading afterglow of the Big Bang, which was stretching further into the infrared with each passing eon. But within that pervasive gloom, the quiet work of gravity had already begun. Those tiny density variations, the seeds imprinted by inflation and mapped in the cosmic microwave background, were regions where dark matter had already begun to clump. Hydrogen and helium gas, now free from the buffeting pressure of radiation, began to feel the gentle, relentless pull of these invisible dark matter halos. It was an achingly slow process. Gas streamed along the filaments of the dark matter web, flowing into the densest knots. As these clouds of primordial gas gathered, they began to collapse under their own weight. But there was a problem. Hydrogen gas, when it gets squeezed, heats up to form a star. This heat needs to be released so the cloud can continue collapsing. In the modern universe, gas clouds contain trace amounts of heavier elements like carbon and oxygen, which help radiate heat away efficiently. The first clouds had none of that. They were made of pure hydrogen and helium, elements that are terrible at cooling. This meant the first protostellar clouds had to grow incredibly massive and dense before their own gravity could overcome the internal heat pressure. The result was a generation of stars unlike any we see today. Astronomers call them population 3 stars. They were behemoths, likely hundreds of times more massive than our Sun. Imagine a star so colossal it would make our sun look like a tiny speck beside it. These giants burned at ferocious temperatures, their surfaces blazing with a fierce blue-white light. Their lives were spectacularly brief. Fueled by such immense reservoirs of hydrogen, they burned through their nuclear fuel in only a few million years, a mere blink in cosmic time. And their deaths were even more consequential. A star that massive does not fade quietly. It ends its life in a cataclysmic supernova explosion of unimaginable power, forging the first heavy elements like carbon, oxygen, and iron, and blasting them out into the surrounding void. But their birth was perhaps their greatest gift to the cosmos. The intense ultraviolet light from these first brilliant stars began to tear apart the neutral hydrogen atoms that filled the universe. The process is called reionization. Photons with enough energy would knock the electrons right off the hydrogen atoms, splitting them back into free protons and electrons and recreating a plasma. This was not an instant flash. It was a gradual, patchy process. Bubbles of ionized gas began to form around the first stars and early galaxies, like bright islands growing in a dark sea. Over hundreds of millions of years, these bubbles expanded and merged, eventually filling the entire universe with a diffuse, ionized plasma once more. This great transformation, the epoch of reionization, lifted the final veil of neutral gas. It made the universe transparent to most wavelengths of light, clearing the path so that the light from all future generations of stars and galaxies could travel across the cosmos unimpeded. The ignition of that first star was a moment of cosmic dawn, ending the long, dark night. It was the moment the universe, which had been a featureless expanse of simple elements, began its long journey toward complexity, forging the very ingredients that would one day form rocky planets, oceans, and life itself. The dawn of starlight was a violent rebirth for the cosmos. The epoch of reionization was not a gentle sunrise, but a storm of radiation that fundamentally reshaped the universe's very nature. For hundreds of millions of years after the cosmic microwave background was released, the cosmos was filled with a fog of neutral hydrogen gas. But when those first, monstrous population 3 stars ignited, they unleashed a torrent of high-energy ultraviolet photons. These photons are the key. A neutral hydrogen atom is simply a proton with an electron bound to it. The intense UV light from the earliest stars and the voracious black holes at the centers of the first galaxies carried enough energy to blast that electron away, a process called ionization. One by one, atom by atom, the neutral hydrogen fog was burned away, split back into its constituent protons and free electrons. This did not happen uniformly. Think of it like a cold, dark landscape slowly being illuminated by the lights of distant cities. The first stars acted as lone beacons. Around each one, a growing bubble of ionized plasma would form. As more stars ignited and the first small galaxies merged and grew, these bubbles expanded and began to overlap, carving out vast, connected regions of transparent space within the neutral sea. Over several hundred million years, these bubbles eventually merged completely, flooding the entire universe with ionized gas once more and ending the cosmic dark ages for good. This process made the universe transparent to ultraviolet and visible light, which had previously been absorbed by the neutral hydrogen. It cleared the final obstacle, allowing light from all future stars and galaxies to travel across the cosmos unimpeded, right up to our telescopes today. But how can we possibly observe an event that happened over 13 billion years ago? The evidence is etched into the light of the most distant objects we can see, quasars. A quasar is the incredibly bright core of a young galaxy, powered by a supermassive black hole devouring matter. Its light acts like a cosmic flashlight beam shining through the universe. When astronomers analyze the spectrum of light from a quasar so distant that its light was emitted during the epoch of reionization, they see something telling. The light shows a distinct absorption pattern, a forest of dark lines. These lines are created by the remaining patches of neutral hydrogen gas that the quasar's light passed through on its long journey to us. By studying how this Lyman alpha forest changes in quasars at different distances, and thus from different eras, astronomers can map the timeline of reionization. They can see when the neutral hydrogen patches were abundant and when they finally vanished, confirming that this great transformation was complete by the time the universe was about 1 billion years old. Reionization was the universe's final major transition, the moment it became the clear, star-filled expanse we recognize today, all sparked by the unforgiving brilliance of its very first stars. The brilliant chaos of reionization was not just clearing a cosmic fog, it was setting the stage for the universe's first great cities of light. How do galaxies form and evolve from that primordial soup? Their story is not one of instant creation, but of a slow, relentless, and often violent construction project spanning billions of years. The process is called hierarchical clustering, a bottom-up assembly where small pieces merge to build something grand. It began with those first dark matter halos, the invisible gravitational anchors that formed from the seeds of inflation. Hydrogen and helium gas, now enriched with the first heavy elements from exploding population 3 stars, flowed into these halos. Within these dense pockets, the gas cooled, fragmented, and collapsed to form not just individual stars, but the first proto-galaxies. These were tiny, faint things by today's standards, perhaps only 1/10,000th the mass of our Milky Way. But they were the foundational bricks. Gravity, the universe's great architect, then went to work. These small proto-galaxies, drawn together along the filaments of the cosmic web, began to dance. They orbited one another, slowly spiraling closer over eons until they collided and merged. 2 small galaxies would smash together, their stars mingling in a vast gravitational waltz that rarely saw actual stellar collisions but dramatically reshaped their structure. This merger would trigger a furious burst of new star formation as the collision compressed vast clouds of gas. Over time, through a repeated cycle of mergers and acquisitions, these building blocks assembled into the majestic spiral and elliptical galaxies we see today. The type of galaxy that results is a record of its violent history. Take a beautiful spiral galaxy like our own Milky Way. Its iconic pinwheel arms, full of young, blue stars and glowing gas clouds, tell a story of relative quiet. It likely grew by steadily consuming smaller dwarf galaxies and slowly accreting gas from intergalactic space, allowing for a long, stable period of star formation. Its rotating disk shape was preserved. Now look at a giant elliptical galaxy, a massive football-shaped collection of mostly old, red stars with very little gas. This is the signature of a more violent past. Ellipticals are thought to be the products of major mergers between 2 large spiral galaxies. When 2 spirals of similar size collide, their orderly disks are utterly destroyed in the gravitational chaos. The stars are thrown into random orbits, creating the smooth, featureless ellipsoid. The collision drives so much gas into the central regions that it sparks an incredible, brief frenzy of star birth called a starburst, which quickly consumes all the available fuel. What remains is a red and dead galaxy, full of aging stars with no gas left to make new ones. At the heart of almost every large galaxy, including our own, lies another key player in this evolutionary drama, a supermassive black hole. These monsters, weighing millions or even billions of times the mass of our Sun, are not just passive occupants, they are active participants. During galactic mergers, vast amounts of gas can be funneled toward the central black hole. As this gas spirals in, it heats up to incredible temperatures, blazing with light as a quasar or an active galactic nucleus. This outpouring of energy can be so intense that it blows away the surrounding gas reservoir, effectively shutting off star formation in the entire galaxy. The black hole, in its ferocious feast, regulates the growth of its own home. This intricate dance between dark matter halos, gas cooling, mergers, star formation, and central black holes has shaped every galaxy we see. Our Milky Way itself bears the scars of this history, with stellar streams in its halo, the ghostly remnants of dwarf galaxies it has consumed, and it continues today. We can see galaxies in every stage of collision and merger across the cosmos, from pairs just beginning their gravitational tango to chaotic wrecks where new identities are being forged. A galaxy is not a static island, but a dynamic creature. Its form a living record of all the collisions, bursts, and quiet periods it has experienced since the dawn of time. These cosmic monsters are not just destructive voids, they are the hidden engines of creation and control. At the very heart of nearly every large galaxy, including our own Milky Way, lies a supermassive black hole. These are not the stellar mass black holes formed from collapsing stars. These are behemoths with masses millions to billions of times that of our Sun, compressed into a region of space no larger than our solar system. Their existence was once pure theory, but the evidence is now overwhelming. The first clue came from the very center of our galaxy. Astronomers have tracked the orbits of stars whipping around an invisible point in the constellation Sagittarius at speeds exceeding 5,000 kilometers per second. Their paths reveal the presence of an object 4 million times the mass of our Sun, packed into a space smaller than the orbit of Mercury. Nothing but a supermassive black hole could explain such extreme gravity. Beyond our galaxy, we see even more dramatic proof. Quasars, the most luminous objects in the universe, are in fact the blazing cores of distant galaxies. Their incredible energy, outshining 1,000 normal galaxies, comes from a supermassive black hole actively feeding on a swirling disk of gas and dust. As matter spirals in at nearly the speed of light, it heats to millions of degrees, glowing brilliantly across the electromagnetic spectrum before vanishing past the event horizon. These active galactic nuclei are the telltale sign of a monster's meal, but their very existence poses a colossal puzzle. We see quasars shining from the universe's infancy when it was less than 1 billion years old. How did black holes grow to billions of solar masses so quickly? It is a cosmic race against time. One theory suggests the first black holes were born from the direct collapse of enormous primordial gas clouds, skipping the star stage entirely to form seeds hundreds of thousands of times the Sun's mass. Another proposes that early, dense star clusters collided and merged their stellar black holes into a giant. However they started, these seeds then began an era of voracious feeding, gorging on the plentiful gas of the young universe and merging with other growing black holes during galactic collisions. Their growth was likely chaotic and explosive, powering the quasars that lit up the early cosmos. Yet, the true wonder of these black holes is not their appetite but their influence. They are not passive occupants, they are regulators. This is the concept of black hole feedback. During its active quasar phase, a supermassive black hole does not consume all the gas that falls toward it. Some of the infalling material gets channeled into powerful, magnetically collimated jets that blast out from the poles at nearly light speed. These jets can travel for hundreds of thousands of light years, plowing into the galaxy's surrounding gas reservoir. The energy they deposit is staggering, heating the gas and blowing it away into intergalactic space. By doing this, the black hole effectively shuts off its own fuel supply and, crucially, halts star formation across the entire galaxy. It is a self-regulating cycle. A merger brings in gas, feeding the black hole and igniting a quasar. The quasar's fury then expels the gas, starving both the black hole and the galaxy of the material needed to make new stars. This feedback explains why we see giant elliptical galaxies that are red and dead, full of old stars but no young blue ones. Their central black holes, in a past frenzy of activity, sterilize them. The monster at the center is both creator and destroyer, a gravitational titan whose violent outbursts sculpt the galaxy around it, dictating its growth, its shape, and ultimately its fate. The universe is not a random scatter of isolated galaxies. Zoom out far enough and a breathtaking architecture emerges, a cosmic web of staggering scale and beauty. This is the large-scale structure of the universe, and it reveals the final, magnificent consequence of those first quantum seeds. On the grandest scales, galaxies are not distributed evenly. Instead, they are strung along immense, thread-like filaments of dark matter, intersecting at dense nodes where enormous galaxy clusters reside. These filaments, light years across, weave through the cosmos, forming a vast three-dimensional spiderweb. And between them lie the great cosmic voids, enormous bubbles of near emptiness that can span hundreds of millions of light years. This sponge-like, frothy structure is the universe's true skeleton. To understand its origin, we must rewind time. Those tiny quantum fluctuations in the inflattened field, the ones imprinted on the cosmic microwave background, were not perfectly smooth. Some regions were ever so slightly denser than others. After inflation stretched these imperfections to cosmic size, gravity began its slow, relentless work. Over billions of years, the slightly denser patches pulled in more dark matter and gas from their surroundings. They grew into the knots and filaments. The slightly less dense regions were drained of material, expanding into the vast, empty voids. The cosmic web is essentially a map of the universe's initial conditions, a fossilized imprint of quantum mechanics writ large across the heavens. Mapping this structure is one of modern astronomy's greatest cartographic endeavors. Projects like the Sloan Digital Sky Survey have spent decades systematically scanning the sky, measuring the positions and distances of millions of galaxies. By plotting these points in 3 dimensions, astronomers have constructed stunning maps of the cosmic web, revealing its intricate filaments and cavernous voids in unprecedented detail. These maps are more than just pretty pictures. They are precise scientific instruments. By measuring how galaxies cluster together on different scales, scientists can perform a cosmic census. The statistical patterns in the web tell us the exact mix of ingredients in the universe, how much ordinary matter, how much dark matter, and how dark energy influences the growth of structure over time. The filaments themselves are not solid threads, but rivers of dark matter along which galaxies flow like leaves on a current. Galaxy clusters, where multiple filaments meet, are the bustling metropolises of the cosmos, home to thousands of galaxies bound together by a common gravitational well. And the voids are not completely empty. They contain a few isolated, lonely galaxies and extremely diffuse gas, but their overwhelming emptiness shapes the flow of the web around them. This grand structure is still evolving today. The gravitational pull of the web continues to guide the motion of galaxies, while the repulsive push of dark energy stretches the voids ever larger, slowly thinning out the great cosmic tapestry over eons. We are living inside a single thread of this unimaginably vast construction, our local group of galaxies just one small part of a filament that eventually leads to the immense Virgo cluster. Our place in the universe is not at the center of anything, but within the delicate strands of a web whose pattern was decided in the first trillionth of a second of time. That magnificent cosmic web, however, is not a permanent cathedral. Its ultimate fate is written in the mysterious nature of dark energy. We have seen how this force is accelerating the expansion of the cosmos, but where does that acceleration lead? The answer depends on the precise character of dark energy, and science outlines several profound and profoundly different endings. The first, and currently the most supported by observations, is the Big Freeze, also known as heat death. In this scenario, dark energy behaves as a true cosmological constant, a steady force inherent to space itself. The acceleration continues at its current, gentle pace. Over trillions of years, galaxies beyond our local gravitationally bound group will be pushed away by the stretching space between us, their light redshifting into invisibility. The observable universe will shrink to a lonely island of a few dozen galaxies. Inside those galaxies, star formation will eventually cease as all the interstellar gas is either used up or blown away. Existing stars will burn through their fuel one by one, flickering out. White dwarfs will cool into black dwarfs, neutron stars will fade, and even the supermassive black holes at galactic centers will, over unimaginable timescales, evaporate via a quantum process called Hawking radiation. The universe will approach a state of maximum entropy, a uniform, frigid sea of diluted particles and radiation, just a fraction of a degree above absolute zero. All energy gradients will be gone, all structure erased. It is a quiet, eternal, and deeply lonely conclusion. But what if dark energy is not constant? What if it strengthens over time? This leads to the most violent finale, the Big Rip. If the repulsive force of dark energy grows powerful enough, it will eventually overcome every binding force in nature. First, the acceleration would tear apart galaxy clusters, then individual galaxies. As the rip approaches, the force would overcome the gravity holding our own Milky Way together, scattering stars into the void. Closer to the end, it would rip apart solar systems, then planets. In the final moments, the force would exceed the nuclear forces holding atoms together, shredding every molecule, every atom, and even the fabric of spacetime itself. The universe would end not with a whimper, but in a catastrophic, fundamental disintegration of reality. There is a third, older possibility that now seems unlikely given our discovery of acceleration, the Big Crunch. This was the classic rival to the Big Freeze. If the density of matter in the universe had been high enough, gravity would have eventually halted and reversed the expansion. Galaxies would begin rushing together, the cosmic background radiation would blue shift and heat up, and the universe would collapse back into a hot, dense state, a mirror image of the Big Bang, potentially ending in a singularity. While current data rules out a simple Big Crunch, it finds new life in a more elegant idea, the cyclic universe. Perhaps our Big Bang was not a beginning but a bounce. In some models, the universe expands, eventually contracts in a Big Crunch, but instead of ending, rebounds into a new expansion phase due to quantum gravitational effects. Each cycle erases the past, but the fundamental constants might reset, leading to an endless series of universes, each with its own laws and potential for life. The fate of everything, every galaxy, every star, every atom hangs on a precise measurement we have not yet made. Is dark energy perfectly constant, or does it evolve? The next generations of telescopes like the Vera C, Rubin Observatory and the Nancy Grace Roman Space Telescope will peer deeper into the past, measuring the expansion history with exquisite precision, hoping to catch dark energy in the act of changing. We are living in the brief, shining epoch where the universe is structured and alive, tasked with discovering whether our story ends in ice, fire, or an eternal rebirth. The silent, ultimate fate of our cosmos forces a question of breathtaking scope. Could our entire universe, with its specific laws and constants, be just one island in a far vaster archipelago of reality? This is the idea of the multiverse, and it emerges not from pure fantasy, but from the edges of our most successful scientific theories. One powerful concept comes from the theory of cosmic inflation. Recall that brief, exponential expansion in the universe's first moments. Some models suggest this inflation is not a one-time event but eternal. In this picture, the inflattened field, that energy that drove expansion, does not settle everywhere at once. Think of a pot of water coming to a boil. Most of the water is bubbling, but here and there a pocket of calm forms as a bubble of steam rises. In eternal inflation, our entire observable universe is one such bubble, a region where inflation ended, allowing for a hot Big Bang and the formation of stars and galaxies. But elsewhere, in the greater boiling background, inflation continues forever. new bubbles are constantly nucleating, giving rise to entirely separate universes with their own big bangs, disconnected from ours by ever-expanding inflationary space. This is a multiverse born from cosmology itself. String theory, a candidate for a theory of everything, suggests another pathway. To make the math of string theory work, it requires extra spatial dimensions, tiny, curled-up shapes at every point in space. The theory allows for a staggering number of possible shapes for these extra dimensions, perhaps 10 to the 500 different configurations. Each configuration yields a different set of physical laws and constants for its universe. This is the string theory landscape, a vast cosmic catalog of possible realities. Our universe, with its specific electron mass and strength of gravity, would correspond to just one possible valley in this immense abstract terrain. Even quantum mechanics offers a multiverse interpretation. In the famous many worlds view, every quantum event with multiple possible outcomes actually happens, but the universe splits into branches for each possibility. A particle's path is not decided. Instead, reality divides, creating parallel timelines for every quantum choice. In this view, every possible history that quantum mechanics allows is real somewhere in the branching multiverse. The implications are profound. If a multiverse exists, the fine-tuning of our universe, the precise values of constants that allow for stars, planets, and life, may not be a miraculous coincidence. In an infinite or near-infinite ensemble of universes, every possible combination of laws is realized somewhere. We simply find ourselves in one of the rare universes capable of supporting conscious observers. This is the anthropic principle in a cosmic context, but is this science or is it philosophy? The central challenge is testability. By definition, these other universes are causally disconnected from ours. No signal, no light, no information can cross the gap. How can we ever prove something we can never interact with? Scientists look for indirect evidence. One possibility is to search for signatures in our own cosmos. If our bubble universe collided with another in the distant past, it might have left an imprint on the cosmic microwave background, a kind of bruise on the sky. Astronomers have searched for such anomalous patterns, though none have been conclusively found. Another approach is to see if the multiverse idea solves other deep puzzles in physics, like the cosmological constant problem, in a more elegant way than any single universe theory. Ultimately, the multiverse pushes at the boundary of the scientific method. It is a prediction of our best theories, yet seemingly beyond empirical reach. Whether it is a profound insight into the nature of reality or a speculative step too far remains one of the most heated debates in modern cosmology, a mystery that asks if our entire reality is merely a local bylaw in a much grander and forever hidden metacosmos. That grand cosmic web, and we ourselves, exist only because of a fundamental imbalance written into the first moments of time. The universe should be empty. According to our best theories, the Big Bang should have created matter and antimatter in perfectly equal amounts. For every proton, there should have been an antiproton. For every electron, a positron. And when matter meets its antimatter counterpart, they annihilate in a flash of pure energy, leaving nothing behind. If symmetry had held, every particle in the early universe would have found its opposite, and the entire cosmos would have dissolved into a uniform sea of radiation. There would be no stars, no planets, no us, yet here we are in a universe made almost entirely of matter. This profound mystery is called baryon asymmetry, and its solution lies in a process known as baryogenesis. Physicists have identified three key conditions that must have been met in the early universe to create this matter surplus. First, there must have been processes that did not conserve baryon number. Baryon number is like a cosmic accounting rule where protons and neutrons get a score of +1 and their antiparticles get -1. In normal reactions, the total is conserved. To create a permanent excess of matter, this rule had to be broken. Second, the universe must have been in a state out of thermal equilibrium. If everything is perfectly balanced and uniform, any particle excess created would just get wiped out. There needed to be a sudden change, a cosmic phase transition that froze in an imbalance before nature could correct it. Third, and most crucial, there must have been a violation of both charge conjugation and parity symmetry, known as CP violation. This is a subtle but profound difference in how matter and antimatter behave. Charge conjugation means swapping every particle for its antiparticle. Parity means looking at the universe in a mirror, flipping left and right. If the laws of physics were perfectly symmetric under both, matter and antimatter would behave identically and no excess could form. But if they are violated, matter can decay or interact at a slightly different rate than antimatter, creating a tiny bias. We have actually observed CP violation in the lab. In experiments with particles called kaons and B mesons, scientists see that their matter versions decay in a slightly different way than their antimatter counterparts. It is a minuscule effect, but it proves the symmetry is broken. The problem is, the amount of CP violation we have measured is far too small to account for the overwhelming amount of matter in the cosmos. So the hunt is on for a much stronger source in the early universe. One leading idea involves a hypothetical phase transition moments after the Big Bang, similar to water freezing into ice. As the universe cooled, a fundamental field called the Higgs field, which gives particles their mass, may have undergone a sudden shift. Bubbles of the new, stable phase would have expanded and collided. At the walls of these colliding bubbles, conditions would have been wildly out of equilibrium, and processes involving extremely heavy particles could have violated baryon number and CP symmetry dramatically, generating the matter surplus before everything settled down. Another fascinating possibility involves the neutrinos, those ghostly particles that barely interact with anything. If neutrinos are their own antiparticles, a special type called Majorana particles, then very heavy, early universe versions of them could have decayed asymmetrically, producing more matter than antimatter as they vanished. Every proton in your body is a survivor of that ancient 1 in a billion imbalance. For every billion matter-antimatter pairs that annihilated in the first second, a single matter particle was left behind. That tiny residue is everything we see. The search for the exact mechanism is one of the great quests in particle physics, probing the energies of the universe's first fractions of a second, where the fundamental rules themselves were being written. That 1 in a billion surplus of matter could only assemble into the complex world we see because of the universe's rulebook, written by 4 fundamental forces. These are the architects of reality, and their story is one of unity, then divorce. In our world today, we experience 4 distinct forces. Gravity is the most familiar, the gentle, long-range pull that holds planets in orbit and shapes the cosmos. Electromagnetism governs light, electricity, and magnetism, binding atoms into molecules and making chemistry possible. Then, hidden within the atomic nucleus are the 2 nuclear forces. The strong nuclear force is the incredible glue that holds protons and neutrons together, overcoming the fierce electromagnetic repulsion between positively charged protons. The weak nuclear force is responsible for certain types of radioactive decay, and it plays a crucial role in how stars burn. These 4 seem utterly different in strength and character. Gravity is incredibly weak compared to the others. A tiny fridge magnet can overcome the entire Earth's gravitational pull on a paperclip, yet physics tells us this was not always so. In the unimaginable heat of the universe's first moments, these 4 forces were not separate. They were believed to be unified into a single, perfect superforce. This is one of the most profound ideas in theoretical physics. Think of it like water. At high temperatures, water is a uniform vapor, but as it cools, it undergoes a phase transition, condensing into liquid and then freezing into solid ice. The fundamental forces behaved similarly. In that first fraction of a second after the Big Bang, when temperatures soared above 10 to the 32 degrees, the energy was so extreme that the distinctions between these forces melted away. Gravity, electromagnetism, and the strong and weak nuclear forces were all aspects of one symmetrical, unified interaction. Particles themselves were likely indistinguishable in that primal fire. As the universe expanded and cooled, this perfect symmetry began to break, a process called spontaneous symmetry breaking. It is like a pencil balanced perfectly on its tip. That state is symmetrical. It looks the same from every direction, but it is unstable. The pencil will eventually fall, choosing one particular direction. The symmetry is broken, but a new, stable state emerges. In the cooling cosmos, as the temperature dropped past certain critical thresholds, the unified force underwent similar phase transitions. First, gravity is thought to have separated from the others, defining the fabric of spacetime itself. Then, at even higher energies than we can currently reproduce, the strong force split from what we call the electroweak force. Finally, as the universe cooled further, the electroweak force itself broke apart into the electromagnetic force and the weak nuclear force we recognize today. Each breaking released energy and shaped the kind of universe that could form. The separation of the electromagnetic and weak forces, for instance, gave mass to particles like the W and Z bosons through the Higgs mechanism, while leaving the photon massless. This is why electromagnetism has an infinite range, governing light and chemistry, while the weak force has an extremely short range confined to the atomic nucleus. We have actually recreated the last of these unifications in particle colliders. By smashing particles together at nearly the speed of light, we can briefly generate energies that mimic the universe's state when it was a trillionth of a second old. In those collisions, the electromagnetic and weak forces merge into a single electroweak force, just as theory predicts. This stunning experimental confirmation gives us confidence that the earlier unifications, though far beyond our current reach, are part of the same cosmic story. The dream of physics is to complete this picture, to find a grand unified theory that describes the merger of the strong force with the electroweak force, and ultimately a theory of everything that includes gravity. Each force we experience today is a frozen fragment of that initial perfection, a relic of a hotter, simpler, and more symmetrical age when the laws of the universe were written in a single, elegant equation. The four forces that govern our reality are actors on a stage, but what is the stage itself? This brings us to a question that cuts to the very heart of existence. What is the true nature of space and time? For centuries, they were considered separate and absolute. Space was a static, three-dimensional container, and time was a universal river flowing at the same rate for everyone, everywhere. Then came Albert Einstein. His theory of special relativity revealed a shocking truth. The rate at which time passes is not absolute. It depends on how fast you are moving. If you could travel at a significant fraction of the speed of light, time would literally slow down for you relative to someone standing still. This is not a theory, it is a measured fact. Atomic clocks flown on airplanes tick slightly slower than their counterparts on the ground. But Einstein's real revolution was general relativity. He proposed that space and time are not just linked, they are fused into a single, four-dimensional fabric called spacetime. And this fabric is not a rigid stage, it is dynamic and malleable. Massive objects like stars and planets warp and curve spacetime around them, like a heavy ball placed on a stretched rubber sheet. What we perceive as the force of gravity is not a pull, but the motion of objects following the curves in this warped geometry. Earth orbits the Sun because it is rolling along a groove in spacetime created by the Sun's mass. This elegant picture of a smooth, continuous fabric works perfectly on cosmic scales. But when we look at the universe at its very smallest scales, a different set of rules takes over. Quantum mechanics, the physics of the atom, paints a far more chaotic picture. In the quantum realm, nothing is certain. Particles exist in clouds of probability, and empty space is a seething, energetic void. This creates a fundamental conflict. general relativity describes a smooth, geometric spacetime, while quantum mechanics demands a frenzied, probabilistic reality. So what does spacetime look like if you could zoom in, not to the size of an atom, but to the smallest possible scale? This scale is known as the Planck length. It is about 1/trillionth of a trillionth the size of a proton. At this unimaginably tiny distance, the smooth fabric of spacetime predicted by Einstein is believed to break down completely. Instead of a calm sheet, the very structure of reality may become a chaotic, turbulent froth. Physicists call this quantum foam. In this realm, spacetime itself would be subject to violent, random fluctuations. Microscopic wormholes might blink in and out of existence. Tiny bubbles of spacetime could form and dissolve. The concepts of here and now lose all meaning. It is a seething ocean of geometry where the smooth continuum we experience is just an average, like the calm surface of the sea hiding a turbulent world beneath. This clash between the smooth cosmos of relativity and the chaotic micro-world of quantum mechanics is the greatest unsolved problem in fundamental physics. We need a theory of quantum gravity, a single framework that can describe how spacetime behaves when it is both incredibly massive, like in a black hole, and incredibly tiny at the Planck scale. The leading candidates for such a theory are string theory and loop quantum gravity. String theory proposes that the fundamental constituents of reality are not point-like particles, but unimaginably small, vibrating strings. The different vibrations of these strings give rise to all the particles and forces, and crucially, they may smooth out the violent fluctuations of quantum foam, providing a consistent description of spacetime at all scales. Loop quantum gravity takes a different approach. It suggests that spacetime itself is not continuous, but is woven from a network of discrete, finite loops. Think of it like a fabric. From a distance, a piece of cloth looks smooth and continuous, but up close you see it is made of individual, interwoven threads. In this view, spacetime has a fundamental graininess, a pixelated structure at the Planck scale. These loops and their connections define the geometry of the universe in a quantum way, potentially preventing the infinities of the quantum foam. The true nature of space and time remains hidden, waiting for a theory that can bridge the vast gap between the cosmos and the quantum. Are we living on a smooth fabric or a tapestry of woven threads? Is the stage of reality a calm geometric plane or a bubbling probabilistic sea? The answer will rewrite our understanding of everything, from the birth of the universe to the fabric of our daily reality. That smooth fabric of spacetime, the stage for all cosmic drama, is not just warped by mass, it has an overall shape. Is our universe infinite and uncurved, or is it a vast, closed sphere? Perhaps it curves away from itself like a cosmic saddle. This geometry is not an abstract curiosity. It dictates whether the cosmos is finite or infinite, and it is written into the total amount of matter and energy the universe contains. General relativity gives us three possible geometries, each linked to a specific cosmic destiny. The first is a flat universe. Picture an endless, perfectly stretched sheet. In this geometry, the rules of Euclid we learned in school hold true. Parallel lines never meet, and the angles of a triangle always add up to 180 degrees. A flat universe has just the precise density, a critical value that perfectly balances the expansion energy against the pull of gravity. This geometry implies the cosmos is most likely infinite in extent. The second possibility is a spherical or closed universe. Imagine the surface of a balloon. This is a positively curved space. On a sphere, parallel lines eventually converge. Think of lines of longitude meeting at the poles. The angles of a triangle add up to more than 180 degrees. A closed universe has a density greater than the critical value. There is so much matter and energy that gravity will eventually overcome the expansion, causing the universe to collapse in a big crunch. This universe would be finite but without an edge like the surface of a sphere. The third shape is hyperbolic or open. Picture a saddle curving away in two directions. This is a negatively curved space. Here, parallel lines diverge, and the angles of a triangle add up to less than 180 degrees. An open universe has a density less than the critical value. Gravity is too weak to ever halt the expansion, so the universe expands forever, thinning out into an infinite cold void. So which one is our home? The answer is etched into the oldest light we can see. The cosmic microwave background is our most precise cosmic blueprint. When scientists measured the size of the temperature fluctuations in that ancient glow, they were looking for a specific signature. In a strongly curved universe, whether spherical or hyperbolic, the light from the Big Bang would have traveled on curved paths. This would magnify or shrink the apparent size of the hot and cold spots on the sky. The observations from satellites like WMAP and Planck were definitive. The fluctuations match the pattern predicted for a perfectly flat universe with astonishing precision. The data tells us the total density of the universe is exactly at the critical value, to within a margin of error of just 0.4%. Our universe is geometrically flat. This has profound and mind-bending implications. A flat universe is balanced on a knife's edge. It suggests the total amount of matter and energy, including the mysterious dark energy, sums to the exact value needed for this perfect geometry. It also strongly implies, though does not definitively prove, that our universe is infinite. If it is flat and has simply connected topology, meaning no tricky twists or loops, then it extends forever in all directions. There would be no boundary, no center, just more galaxies, stars, and potentially even copies of you stretching out without end. This flatness is also a powerful echo of the inflationary epoch. Remember, inflation's explosive stretch would have smoothed any initial curvature, ironing the universe into the flat geometry we observe today. So the shape of our cosmos is not just a static fact. It is a direct message from its first moments, a frozen record of an ancient, violent smoothing, and a guide to its ultimate, accelerating fate. That perfect flatness is a cosmic balance sheet, but the numbers on it are telling a confusing story. How fast is the universe expanding right now? This is measured by a single, crucial number called the Hubble constant. It is the rate at which galaxies are moving away from us, and it has been a cornerstone of cosmology since Edwin Hubble first discovered the expansion nearly a century ago. Determining its precise value is not just about measuring a speed. It is the key to unlocking the universe's age, its size, and its ultimate fate. But today, this foundational number is at the center of a growing crisis, a discrepancy so stubborn it is shaking the very pillars of our cosmic understanding. This is the Hubble tension. The problem is this: we have two powerful, independent ways to measure the Hubble constant. The first method looks back to the universe's infancy. By studying the detailed patterns in the cosmic microwave background, the afterglow of the Big Bang, we can use our well-tested model of the early universe to predict how fast it should be expanding today. This is a pristine, ancient measurement, a direct line to the cosmos at 380,000 years old. The second method measures the expansion rate in our local, modern universe. Astronomers use what are called cosmic distance ladders. They start with nearby stars like Cepheid variables whose pulsating brightness reveals their true distance. They then use those stars to calibrate the distance to galaxies that contain another type of standard candle, type 1, a supernova. By measuring how fast those distant supernovae are receding, they get a direct present-day measurement of the Hubble constant. Both methods are incredibly sophisticated, backed by Nobel Prize-winning science and decades of refinement. The trouble is, they disagree. The early universe measurement from the Planck satellite gives a Hubble constant of about 67.4 kilometers per second per megaparsec. The late universe measurements, most recently from projects like the SOES team using the Hubble Space Telescope, give a value around 73 kilometers per second per megaparsec. The difference is only about 6, which might not sound like much, but the uncertainty in each measurement is so small that the gap is now over 5 standard deviations apart. In science, that is not a discrepancy, it is a chasm. It means the chance this is a simple statistical fluke is less than 1 in a million. So what is going on? There are 2 broad possibilities. The first is that there is some hidden systematic error in one or both measurements, some subtle calibration issue we have not yet caught. Astronomers have checked and rechecked, but so far no obvious error has emerged. The second and far more exciting possibility is that this tension is real and it is a clue pointing to new physics. Our standard model of cosmology, called lambda cold dark matter, might be incomplete. Perhaps dark energy is not a constant but is evolving and strengthening over time. Maybe there is an unknown type of neutrino or another exotic particle that was present in the early universe and changed its expansion history. Or perhaps dark matter has properties we do not yet understand. This puzzle is so important because it is a direct empirical challenge to our best model of reality. It is a crack in the foundation, and through that crack we might glimpse something profound. The Hubble tension is not just a debate about a number. It is the universe giving us a hint that our story, as elegant as it is, might need a new chapter. The race is on to resolve it, with new telescopes and missions designed to measure the expansion with even greater precision. The answer will either reaffirm our cosmic model or force us to rewrite it, revealing a universe that is stranger and more dynamic than we ever imagined. The precise value of the Hubble constant is a modern puzzle, but the ingredients it measures have existed since the first fraction of a second. What were the very first particles to emerge from the cooling fireball of the Big Bang? To answer that, we must journey to a time before atoms, before even protons and neutrons existed, when the universe was a seething, exotic soup unlike anything in existence today. In the first microseconds, the temperature was so high, trillions of degrees, that the fundamental building blocks we know were melted into a more primordial state. This state is called the quark-gluon plasma. Imagine a universe so energetic that it was not filled with solid particles, but with a dense, churning liquid of pure energy and freedom. Quarks, which are the constituents of protons and neutrons, and gluons, the particles that carry the strong nuclear force, roamed freely. They were not bound together. In this extreme heat, the strong force that normally locks quarks into permanent confinement was overcome. The entire cosmos was a blinding, opaque fluid of these liberated particles, constantly colliding and interacting. It was a perfect, frictionless liquid, the hottest and densest substance nature can produce. This was the universe's first tangible state of matter, but this freedom was fleeting. As the cosmos expanded, it cooled with breathtaking speed. Within mere microseconds, the temperature dropped below a critical threshold, about 2 trillion degrees. Suddenly, the strong nuclear force could reassert its grip. It was like a phase change, similar to water vapor condensing into liquid droplets. The free-roaming quarks and gluons began to feel an irresistible pull toward one another. They started to clump together in groups. Quarks bound in trios to form protons and neutrons, which physicists collectively call hadrons. Gluons, the carriers of the force, became the glue that permanently held these trios together. This process, known as hadronization or quark confinement, happened everywhere at once. In an instant, the universe-wide quark-gluon plasma froze into a hot, dense soup of protons, neutrons, and their antimatter counterparts. This was a perilous moment. Most of these newly formed matter and antimatter particles immediately annihilated each other in a storm of gamma rays, leaving behind only the tiny surplus of matter that makes up our world. But could there have been particles even more fundamental appearing before this quark-gluon epoch? Many theories suggest yes, pointing to hypothetical relics that might still haunt the cosmos today. In the first fractions of a second, at energies far beyond what our particle colliders can reach, physics may have been governed by a single unified force. As that force broke apart, it could have generated exotic, super-heavy particles that decayed almost instantly. Among the most intriguing possibilities are particles that might solve our dark matter mystery. Two leading candidates are WIMP and actions. WIMP, or weakly interacting massive particles, are theoretical heavy particles that would have been produced in great numbers in the early universe's heat. They interact only through gravity and the weak nuclear force, making them nearly invisible, yet their sheer mass could account for the gravitational pull of dark matter. Actions are a different idea, conceived to solve a puzzle in particle physics unrelated to dark matter. They are predicted to be incredibly light, ghostly particles that could flow through the universe in vast numbers, forming a pervasive cold field. Both WIMP and actions, if they exist, would be cosmic fossils, frozen into the fabric of the universe during its first second, unchanged for over 13 billion years. They would be direct messengers from an era of unimaginable energy, a time when the laws of physics themselves were taking their final, familiar form. So the next time you look at your hand, remember that the protons in your atoms are triplets of quarks that once swam freely in a universal ocean of liquid fire, and that the space around you may be filled with a sea of ancient, invisible particles whose birth predates even the existence of light itself. Those first particles were forged in a fire so violent it should have left more than just heat and light. It should have shaken the very fabric of reality, sending tremors through space-time that would echo forever. Can we see evidence of the universe's birth in gravitational waves? To answer, we must understand what these waves are. Think of space-time not as a static stage, but as a vast, flexible membrane. When massive objects accelerate like two black holes spiraling into each other, they create ripples in this membrane, warping the distances between points as they pass. These are gravitational waves predicted by Einstein over a century ago and finally detected directly in 2015. That detection was a monumental triumph, but it opened a door to an even grander possibility. The most cataclysmic events in the cosmos, like black hole mergers, create powerful but fleeting waves. What if there is a permanent, whisper-thin hum underlying it all? This is the idea of the primordial gravitational wave background. It would not come from stellar collisions, but from the birth pangs of the universe itself. The leading candidate for its source is cosmic inflation, that explosive expansion in the first trillionth of a second. The theory suggests that the same quantum fluctuations that seeded galaxies would have also generated powerful ripples in spacetime itself. While the density variations became the cosmic microwave background, the gravitational ripples would have traveled unimpeded through the hot, opaque plasma of the early universe, carrying a pristine signal from a time before light could even travel freely. Detecting this ancient hum would be the ultimate smoking gun for inflation, a direct probe of the universe when it was a mere fraction of a second old. It would allow us to hear the moment of creation, but how do you listen for a whisper from the beginning of time? The signal would be incredibly faint, a stochastic background, a chaotic sea of overlapping waves from all directions, like hearing the roar of a distant ocean in a shell. One promising method uses the universe's most precise natural clocks, pulsars. These are rapidly spinning neutron stars that beam radio waves with metronomic regularity. Astronomers monitor networks of these millisecond pulsars across our galaxy, looking for correlated timing delays. As a gravitational wave passes between Earth and a pulsar, it minutely stretches and squeezes the space, causing the pulsar's ticks to arrive slightly early or late. By looking for a common pattern of shifts across many pulsars, projects like the North American Nanohertz Observatory for Gravitational Waves, or NanoGrav, are hunting for the low-frequency rumble from supermassive black hole binaries. The hope is that within this signal, they might one day tease out the even lower frequency signature of the inflationary background. The future, however, lies in space. The Laser Interferometer Space Antenna, or LISA, is a planned mission that will form a giant triangle of 3 spacecraft trailing Earth in its orbit around the Sun. With arms millions of kilometers long, it will be sensitive to a different band of gravitational waves, one that could potentially contain the direct imprint of cosmic inflation or other exotic processes from the universe's first second. Finding this signal would be like discovering the cosmic microwave background all over again, but for a time before there was any light at all. It would open a completely new window onto the universe's violent infancy, letting us test theories of quantum gravity and perhaps even glimpse what, if anything, came before our Big Bang. The hunt for these primordial ripples is a search for the universe's first vibration, a faint tremor in the dark that says this is how it all began. The violent tremors of inflation did more than just stretch space-time. They magnified a ghostly whisper from the quantum void into the blueprint for reality itself. How can something come from nothing? The answer lies in the bizarre rules of the quantum world, where empty is a very busy place. At the heart of this is Heisenberg's uncertainty principle. It states that on the tiniest scales, certain pairs of properties like energy and time cannot both be known with perfect precision. There is always a fundamental fuzziness. One profound consequence is that the energy of a system, even a perfect vacuum, is not fixed at zero. It fluctuates. For fleeting moments, the universe can borrow energy as long as it pays it back quickly. This loan allows for the spontaneous creation of particle-antiparticle pairs, an electron and a positron, for example, that flicker into existence and then annihilate each other almost instantly. This ceaseless, frothing activity is called quantum fluctuation. The vacuum of space is not empty. It is a seething, probabilistic sea of potential, alive with these virtual particles dancing at the edge of reality. In the ordinary universe, these fluctuations are microscopic and ephemeral. But in the first instance after the Big Bang, during the inflationary epoch, something extraordinary happened. The inflattened field, that energy driving the hyper-expansion, was also subject to quantum uncertainty. Tiny, random fluctuations in its energy density were inevitable. Normally, these quantum jitters would have been insignificant, vanishing as quickly as they appeared. But inflation acted like a cosmic amplifier of unimaginable power. As space expanded exponentially faster than light, those infinitesimal quantum fluctuations in the inflattened field were stretched across the cosmos. Regions where the field was slightly more energetic expanded a tiny bit faster. Regions where it was slightly less energetic expanded a tiny bit slower. These differences were frozen into the fabric of space-time as minute variations in the density of the universe. The microscopic became macroscopic. When inflation ended and the universe reheated, these stretched quantum ripples were imprinted on the hot, dense plasma as regions of slightly higher and lower density. They were the first structures in the cosmos not made of matter but of pure geometry, a pattern of dense and sparse written into the fireball. This is the breathtaking link. The same quantum uncertainty that allows a particle to pop out of nothing in a lab for a fraction of a second also created the seeds for galaxies. After recombination, gravity got to work on these seeds. The slightly denser patches had a bit more gravitational pull. Over hundreds of millions of years, they drew in more dark matter and gas from their surroundings, growing ever larger. The greatest of these density peaks became the sites where the first stars ignited and where galaxies eventually formed. The sparser regions evolved into the vast cosmic voids. Every galaxy cluster, every filament of the cosmic web, and every immense empty space can trace its lineage back to a random quantum twitch in the inflattened field, magnified to a cosmic scale. So when you look at the majestic structure of the night sky, you are not just looking at stars and gas. You are looking at quantum mechanics written in light, at microscopic probabilities stretched into a cathedral of galaxies. The grand architecture of everything began not with a bang, but with a whisper, a quantum fluctuation that the universe, in its violent youth, chose to make permanent. This deep uniformity is a clue written in the oldest light, but it is also one of the universe's most puzzling features. Why is the cosmos so incredibly smooth? Look in any direction, and the temperature of the cosmic microwave background is the same to within a tiny fraction of a degree. This near-perfect uniformity is strange, because according to the standard Big Bang model without inflation, it should be impossible. This is the horizon problem. Think of 2 cups of coffee, one placed in a kitchen in Paris and another in a kitchen in Tokyo. If you come back an hour later and find they have both cooled to exactly 60 degrees Celsius, you would assume they had been in contact, or at least that someone had coordinated their temperatures. But if you knew they had been isolated from the moment they were poured, their identical temperature would be a profound mystery. The cosmic microwave background presents us with exactly this mystery on a universal scale. Regions of the sky on opposite sides of the universe, billions of light years apart, have the same temperature. The problem is one of causality, of cause and effect. Nothing can travel faster than light. In the standard Big Bang story, the universe was about 380,000 years old when the cosmic microwave background was released. In all that time, light could only have traveled a finite distance, creating a sphere of influence around any point called the particle horizon. 2 regions on opposite sides of today's sky were far outside each other's particle horizons back then. They were causally disconnected. They had no way to exchange heat or information to equalize their temperatures. It is as if those 2 cups of coffee, never having met, somehow knew to cool to the exact same degree. This is the horizon problem, and for decades it suggested the universe began in a state of inexplicable, fine-tuned uniformity, a cosmic assumption with no explanation. The theory of inflation provides the elegant solution. It proposes that these 2 distant, seemingly disconnected patches of sky were once intimately connected. In the universe's first unimaginable fraction of a second before inflation, the entire observable cosmos was crammed into a region trillions of times smaller than a proton. At that scale, every part of the universe was in direct causal contact. It was like a single, tiny, superheated droplet. Particles and energy could bounce around and interact freely, allowing the entire region to reach a perfectly uniform temperature, a state of thermal equilibrium. Then inflation struck. In that fleeting instant of hyper-expansion, this tiny, uniform droplet was stretched to a size larger than our entire observable universe today. Regions that were once neighbors were violently pushed apart, ending up on opposite sides of the cosmos. The uniformity was not created by inflation. It was inherited from that initial, connected state and then locked in by the rapid stretching. Inflation took a small, causally connected region and blew it up to become everything we can see, carrying its perfect smoothness across the vastness of space. The horizon problem vanishes. The matching temperature of distant skies is not a mysterious coincidence, but a fossil of a time when those skies were pressed together, before the universe inflated them into distant strangers. This is the power of a good scientific idea. It takes an apparent flaw in our story, a nagging why that seems to require magic, and reveals it instead as a natural consequence of a deeper, more fundamental process. The uniformity of the cosmos is not a starting assumption. It is a prediction, a direct echo from a time when all of reality was smaller than a single point of light. That perfect smoothness is only half the story of inflation's magic. The universe is not just uniform, its geometry is perfectly flat, and this presents an even more baffling puzzle. Why is the cosmos so flat? This is known as the flatness problem, and it reveals a universe balanced on a razor's edge. For the universe to appear flat today, 13.8 billion years after the Big Bang, its initial conditions had to be fine-tuned to an almost impossible degree of precision. Imagine trying to balance a pencil perfectly on its tip. The slightest breath of wind, the tiniest vibration, and it will fall over. The universe's geometry is like that pencil. In the equations of general relativity, the fate of cosmic geometry is a tug-of-war between the outward momentum of the Big Bang and the inward pull of all the matter and energy. There is a precise, critical density that perfectly balances these two, resulting in a flat universe. If the actual density at the beginning was even a hair above this critical value, the universe would be positively curved like a sphere. Gravity would dominate and the cosmos would have collapsed back in a big crunch long ago. If the density was a hair below, the universe would be negatively curved like a saddle, and it would have expanded so rapidly that galaxies and stars could never have formed. We would have a cold, empty, hyperbolic void. For our universe to be as flat as we measure it today, its density at 1 second after the Big Bang had to be equal to the critical density to within 1 part in 10 to the power of 15. That is a precision of 0.0000000000001%. It is like aiming for a bullseye the size of an atom from 1,000 light years away. This level of fine-tuning seems absurd, a cosmic coincidence begging for an explanation. Once again, inflation provides the answer, and it does so with breathtaking elegance. Think of the surface of a balloon. If the balloon is small, its curvature is obvious, it is clearly a sphere. But now, imagine inflating that balloon to an enormous size. If you were an ant standing on its surface, your tiny patch of the balloon would appear perfectly flat. Inflation did exactly this to the entire observable universe. Before inflation, the universe could have had any amount of curvature. It could have been a tightly crumpled sphere or a wildly twisting saddle. But then, in a fraction of a second, inflation stretched a tiny, smooth patch of that initial geometry by a factor of at least 10 to the 26. This exponential expansion magnified a microscopic region into a volume larger than everything we can see. From our perspective inside that stretched patch, the curvature is undetectable. The universe appears perfectly flat, just as the surface of the Earth feels flat to someone standing in a field. Inflation did not make the universe flat by fine-tuning. It made our observable universe flat by taking a tiny, possibly curved piece of the whole and stretching it so much that any initial curvature was smoothed out beyond our ability to measure. It transformed a mysterious, razor's-edge fine-tuning into a natural, inevitable outcome of a rapid, early-growth spurt. The flatness we measure is not a clue to the universe's global shape, which may still be curved on scales far beyond our horizon. It is a local artifact, a fossil of that ancient stretching, telling us that we are living inside a tiny piece of a much larger reality that was blown up to become our entire cosmic home. This razor's edge of flatness relies on a precise cosmic budget, but one number in that budget defies all understanding. The cosmological constant problem is not just a puzzle. It is a screaming contradiction at the very heart of physics, a gap so vast it suggests we are missing something fundamental about reality. The problem begins with empty space. In quantum field theory, the vacuum is not empty. It is a seething foam of virtual particles constantly flickering in and out of existence. Every possible quantum field contributes a tiny bit of energy to this background hum. When physicists try to calculate the total energy density of this quantum vacuum, they sum up all these infinite contributions. The result is a number of staggering magnitude. This predicted vacuum energy should act as a cosmological constant, a constant energy density inherent to space itself that would drive the expansion of the universe. The trouble is, the number they get is catastrophically wrong. The theoretical prediction is larger than the observed value of dark energy by a factor of 10 to the power of 120. That is a 1 followed by 120 zeros. It is the most spectacular failure of a prediction in the history of science. To grasp this absurd discrepancy, imagine calculating the weight of a single electron based on the best theories we have. Your equations tell you it should weigh as much as the entire observable universe. You would not think the electron is strangely light. You would know your calculation is nonsense. That is the scale of the cosmological constant problem. The vacuum energy we predict should be so immense that it would have ripped the universe apart in a violent explosion within the first fraction of a second, preventing any atoms, stars, or galaxies from ever forming. Yet we exist. Our observations show the actual cosmological constant, which we call dark energy, is incredibly small but not zero. It is a faint, gentle pressure that only began to dominate the cosmos billions of years after the Big Bang. Reconciling these two numbers, the colossal prediction and the tiny observation, is arguably the single most important unsolved problem in theoretical physics. It points to a deep flaw in our understanding. Either our theory of the quantum vacuum is profoundly incomplete, or our theory of gravity, general relativity, breaks down when applied to the vacuum energy, or there is some exquisite, unseen cancellation mechanism that makes nearly all that quantum froth cancel out, leaving behind only the faint whisper we detect. This is not just an academic headache. Solving it is a primary goal for any theory of quantum gravity, like string theory or loop quantum gravity. These frameworks must explain why the vacuum energy is so infinitesimally small, or why gravity ignores almost all of it. Some ideas propose that the many possible vacuum states in string theory's landscape mean our universe simply happens to be one where the net cosmological constant is almost zero, by sheer chance in a multiverse. Others suggest a new symmetry principle or a dynamic field that adjusts to cancel the vacuum energy. The cosmological constant problem is a stark reminder that our two most successful theories, quantum mechanics and general relativity, when combined, produce an answer that is not just slightly off but unbelievably, impossibly wrong. It is a beacon in the dark, illuminating the chasm in our knowledge and challenging us to find a deeper truth that can make sense of a universe built on nothing. The stability of reality itself rests on a few unchanging numbers. We have built our entire understanding of the cosmos on the assumption that the laws of physics are universal and constant. The speed of light in a vacuum, the strength of gravity, the charge of an electron, these are the fixed pillars upon which we have constructed theories from quantum mechanics to cosmology. But what if those pillars are not as solid as we think? Could the very constants of nature be slowly changing over cosmic time? This is not a question of minor tweaks, it is a challenge to the foundation of science itself. One of the most scrutinized constants is the fine structure constant, often denoted by the Greek letter alpha. This number is a pure, dimensionless combination of other constants, the charge of the electron, the speed of light, and Planck's constant. It governs the strength of the electromagnetic force, dictating how tightly electrons bind to atomic nuclei. It controls the energy levels within atoms and the very color of the light they emit or absorb. If alpha were different, chemistry would be different. The stability of molecules, the very possibility of life as we know it, hinges on its precise value. For decades, physicists assumed alpha was, well, constant. But in the late 1990s, a team led by astronomer John Webb began analyzing the light from incredibly distant quasars. As this light travels for billions of years to reach us, it passes through ancient clouds of intergalactic gas. Atoms in these clouds absorb specific wavelengths of the quasar's light, creating a distinctive pattern of dark lines in the spectrum, a chemical fingerprint. Webb's team made a startling claim. The absorption lines from certain atoms, like iron and magnesium, appeared shifted relative to expectations in a way that suggested the fine structure constant was slightly smaller billions of years ago. The change they reported was minuscule, a few parts in a million, but if true, it would be revolutionary. The implications are staggering. A varying constant would mean the laws of physics are not written in stone but in something more fluid. It would suggest that the universe's rulebook evolves. The strength of electromagnetism, which dictates the structure of every atom and molecule, would have been subtly different in the past. This could alter our interpretation of the cosmic microwave background, the process of Big Bang nucleosynthesis, and the observed ages of the oldest stars. Our entire cosmic chronology might need revision. The evidence, however, remains hotly contested. Other teams using different telescopes and methods have failed to confirm the signal or have even found hints of a change in the opposite direction. The measurements are at the very edge of our technological capability, susceptible to incredibly subtle systematic errors. Could the observed shifts be due to unknown properties of the intervening gas clouds or imperfections in our instruments? The scientific community is deeply divided, and the hunt for definitive proof is more intense than ever. If constants do vary, we must ask why. What mechanism could alter the bedrock of reality? Some theories, like certain models of string theory, naturally predict that what we see as constants are actually dynamic fields that have slowly settled to their current values as the universe expanded and cooled. In this view, the speed of light or the strength of gravity might be the outcome of a cosmic relaxation process, not an eternal decree. The search for answers continues, pushing our telescopes to their limits and our theories to the breaking point. Whether the constants are truly constant is more than a technical debate. It is a question about the nature of reality itself. Are we living in a universe with fixed, eternal rules, or in one where the rules themselves are part of the story, slowly written across the canvas of time? The light from those ancient quasars holds the answer, a faint signature waiting to be read. The constants of nature may be the universe's rulebook, but black holes are its ultimate enforcers, and they are hiding a secret that threatens to rewrite the rules entirely. This is the black hole information paradox, a conflict so deep it pits our two greatest theories, quantum mechanics and general relativity, against each other in a battle with reality itself at stake. It begins with a stunning prediction by Stephen Hawking in the 1970s. Using quantum theory near a black hole's event horizon, he calculated that black holes are not completely black. They should glow with a faint heat, now called Hawking radiation. Here is how it works. The quantum vacuum near the event horizon is a storm of virtual particle pairs popping in and out of existence. Normally, they annihilate each other instantly, but if one of the pair falls just across the event horizon while the other escapes, the escaping particle becomes real, stealing a tiny bit of the black hole's mass energy. To an outside observer, it looks like the black hole is emitting a faint thermal glow of particles. This radiation is incredibly weak for a stellar mass black hole, but it has a devastating consequence. It means black holes slowly lose mass and evaporate. Over timescales far longer than the current age of the universe, a black hole will eventually shrink and, according to Hawking's original math, vanish in a final burst of radiation. This is where the paradox explodes. The radiation Hawking predicted is purely thermal, like the glow from a hot stove. It contains no information about what fell into the black hole. Whether you threw in a library of books, a star, or 100 elephants, the outgoing radiation would look exactly the same, a featureless heat signature. This violates a sacred principle of quantum mechanics, the law of unitarity, which states that information is never destroyed. In the quantum world, information about the state of a system, the precise arrangement of all its particles, must always be preserved. You should, in principle, be able to run the clock backwards and reconstruct what went in. If a black hole evaporates completely into random heat, that information is lost forever. Gone, this creates an impossible choice. Either quantum mechanics is wrong and information can be destroyed, which unravels the foundation of all modern physics, or general relativity is wrong and something must happen to preserve the information. For decades, this was the standoff. Hawking famously bet that information was lost, a position that horrified many of his colleagues. The implications are metaphysical. If information can vanish, it erases history, cause and effect break down, the universe becomes fundamentally unpredictable. This is not just about black holes, it is about whether the past has a permanent record. The search for a solution has driven theoretical physics into wild new territories. One leading idea is that the information is not lost, but is somehow encoded on the event horizon itself. The holographic principle suggests that all the information about everything that falls into a black hole is smeared like a hologram onto its two-dimensional surface. When Hawking radiation escapes, it is subtly imprinted with this information, like a scrambled message in the static. The problem is, from the outside, this information would be utterly encrypted and inaccessible until the black hole's final moments, creating another puzzle. Another, more radical proposal is that black holes do not have a true interior at all. The event horizon might be a fiery wall of energy, a firewall that instantly incinerates anything that crosses, preserving information at the boundary but demolishing Einstein's picture of someone smoothly falling in. This idea is deeply controversial, as it suggests a drastic revision of spacetime itself. The most recent progress comes from studying the intricate geometry of spacetime using tools from string theory. This work suggests that the interior of a black hole and the radiation it emits might be profoundly connected through quantum entanglement, forming a complex bridge that preserves information in a way we are only beginning to comprehend. The information paradox forces us to confront the fact that our understanding of spacetime, information, and reality is incomplete. It asks whether the universe keeps perfect records and what truly happens to history when it meets the most powerful destroyer we know. The answer will not just tell us about black holes, but about the very fabric of cause, effect, and time in our cosmos. The fate of reality depends on the silent, steady pull of a ghost. Two starkly different endings loom in our cosmic future, each dictated by the subtle behavior of dark energy. The first is the Big Freeze, also known as heat death. In this scenario, dark energy remains a constant force, as our current best measurements suggest. The acceleration of the universe's expansion continues at its present gentle pace. Over trillions of years, the consequences unfold with a chilling inevitability. Star formation will first cease as galaxies run out of the raw hydrogen gas needed to forge new suns. The existing stars will burn through their fuel one by one, flickering out. Red dwarfs, the longest-lived stars, will finally sputter into darkness after tens of trillions of years. The cosmos will grow dimmer. Galaxies beyond our local gravitationally bound group will be pushed away by the stretching space, their light redshifting into invisibility until our sky is black and empty, save for the fading embers of our own galactic neighborhood. Then, over timescales so vast they defy comprehension, even the remnants will decay. Planets will drift from their orbits. Black holes, once thought to be eternal, will slowly evaporate via Hawking radiation, emitting their final, faint whispers of particles. Protons themselves, the building blocks of atoms, may decay, though this remains unproven. The universe will approach a state of maximum entropy, a uniform, frigid sea of diluted photons and subatomic particles, just a fraction of a degree above absolute zero. All structure, all energy gradients, all difference will be erased. It is a quiet, eternal, and profoundly lonely conclusion, a cosmos where time loses all meaning and nothing ever happens again. But dark energy might not be so constant. If it strengthens over time, a far more violent and dramatic finale awaits: the Big Rip. In this scenario, the repulsive force of dark energy grows in power, eventually overcoming every binding force in nature. It would not be a slow fading, but a catastrophic shredding of reality itself. The timeline is horrifying. Roughly 60 million years before the end, the accelerating expansion would first tear apart galaxy clusters, scattering their members into the void. Then, about 3 months before the final moment, the force would overcome the gravity holding our own Milky Way together. Stars would be flung apart into the endless dark. In the last minutes, solar systems would be ripped apart, planets would be torn from their stars, an instant before the end, Earth itself would be vaporized. Then, in the final microsecond, the repulsive force would exceed the very forces that hold matter together. It would overcome the electromagnetic bonds that bind molecules, shredding every cell, every molecule. It would then surpass the strong nuclear force that holds atomic nuclei together. Every atom in what was once the universe would be blasted apart into a spray of fundamental particles. Finally, space-time itself, the fabric of reality, would be torn asunder. The universe would end not with a whimper, but in a fundamental, catastrophic disintegration. The difference between these two fates is the difference between an eternal, frozen silence and a sudden, ultimate scream. One is a slow dissolution into nothingness, the other a violent unraveling of the very threads of existence. Both hinge on a single, unanswered question. Is the dark energy that fills the vacuum of space a true constant, or does it hide a terrifying capacity to grow? Our cosmic destiny, written in ice or in fire, awaits its final measurement. The universe's final fate, whether a frozen silence or a violent rip, may not be the end of the story. Our 30th and final question dares to look beyond that horizon. Can a new universe be created? This is not science fiction, but speculative physics that follows our deepest theories to their logical and astonishing extremes. One compelling idea connects the end of one cosmos to the birth of another. Inside a black hole, matter is crushed toward a point of infinite density, a singularity. Our physics breaks down there, but some models suggest that instead of ending in oblivion, this singularity could be a bridge. The immense warping of space-time might be so severe that it pinches off, forming a separate region of space-time disconnected from our own. In this view, the interior of a black hole could give rise to an entirely new, expanding universe, a baby universe budding off from our own. From our perspective, everything that falls in is lost forever. But from the inside of that black hole, the event horizon would appear as a cosmic horizon of a new Big Bang, a white hole spewing out matter and energy in a fiery genesis. Our universe in this speculative picture could itself be the interior of a black hole in a parent cosmos, part of an infinite chain of cosmic reproduction. Another terrifyingly beautiful possibility comes from the nature of the vacuum itself. We think our universe sits in a stable, low-energy vacuum state. But what if it is only metastable, like a ball resting in a shallow valley, not at the very bottom of the hill? A rare quantum event, a high-energy collision in a particle accelerator or a spontaneous fluctuation, could theoretically kick the Higgs field into a lower energy state. This event would create a bubble of true vacuum. This bubble would expand at the speed of light, its walls rewriting the laws of physics as they pass. The fundamental constants, the strength of forces, even the number of dimensions would change instantly. Inside this new bubble, a new universe with entirely different physical laws would be born. From our perspective, it would be an unstoppable wave of annihilation, a cosmic reboot erasing our reality in an instant. Yet from the inside of that bubble, it would simply be the beginning of everything. This is the concept of false vacuum decay, a reminder that the ground beneath our feet, the very stability of matter, might be a temporary and fragile state. There is an even more profound idea called cosmological natural selection proposed by physicist Lee Smolin. It suggests a form of cosmic evolution. If black holes give birth to new universes, then those daughter universes could inherit, with slight random variations, the physical constants of their parent. Universes that produce more black holes would have more offspring. Over countless generations, universes would be naturally selected for traits that maximize black hole production. In this stunning vision, the fine-tuning of our constants, the strength of gravity, the mass of the electron, might not be a miracle or a multiverse accident. They could be the result of a blind, cosmic evolutionary process, favoring universes that are efficient factories for making more universes. We might live in a universe optimized for black holes, with stars, galaxies, and planets being mere byproducts of that reproductive drive. These ideas push at the very limits of science, blurring the line between physics and philosophy. They are not yet testable predictions, but they are logical extensions of our best theories, asking what happens when gravity and quantum mechanics meet at their most extreme. They transform the cosmos from a single, lonely narrative into a potential ecosystem of realities, a branching tree of existence where death gives way to birth, and where the laws of nature themselves might be shaped by a timeless process of cosmic selection. As we reach the end of our 30 questions, we are left not with a final answer, but with a profound sense of wonder. From a quantum whisper to a cosmic web, from the unity of forces to the mystery of dark energy, the story of our universe is one of breathtaking beauty and endless mystery. We are part of that story, made from stardust, living on a pale blue dot, and gifted with the curiosity to look up and ask why. The formation of the universe is not a solved puzzle, but an ongoing conversation between human imagination and the silent, majestic cosmos. And that conversation, that search for understanding, is perhaps the most remarkable thing the universe has ever created. The journey we have just taken is almost impossible to grasp. From a single quantum fluctuation to a universe of 1 trillion galaxies, the story of creation is the most magnificent narrative ever told. We have traced the cosmos from its first impossible second, through the forging of the first elements, the silent sculpting by dark matter, and the brilliant dawn of starlight. We have seen galaxies collide and black holes roar, felt the strange push of dark energy, and peered into futures of ice or fire. Yet with every answer, the universe has revealed a deeper, more profound mystery. The trigger for the Big Bang, the true nature of dark matter, the shocking fine-tuning of the constants, these are not solved puzzles but open doors. Cosmology is not a finished book of facts. It is a living, breathing conversation at the very edge of human understanding, a story that is constantly being rewritten with each new telescope, each new experiment, each new bold idea. This is the true gift of looking up. The night sky is not just a beautiful spectacle. It is the ultimate mystery novel written in light and gravity, and we have only just begun to read the first chapter. So the next time you find yourself under a clear, dark sky, remember what you are a part of. You are made of atoms forged in the hearts of long-dead stars, riding a planet around one star among billions, in a galaxy that is just one thread in a cosmic web spanning the observable universe. Your curiosity is the universe's way of understanding itself. Keep asking questions, keep looking up with wonder, and if you want to join us as we keep exploring these great mysteries from the quantum to the cosmic, be sure to subscribe. The story is far from over, and the next discovery could